Hi guys, it's Miss Sheehan, and we are about to go over our water potential and solute potential solutions in our practice sheet here. So have those out, they're in your notes, all except for maybe the second half. Okay, first, let's just look at some numbers, looking at solute and molarity and like how things are going to move around. We're not using any equations yet, so let's just look at our question. And first, we're looking at an artificial cell, which is just a little bag, maybe an artificially selectively permeable membrane, and that's actually what we're going to be doing in lab. So this is kind of simulating what we'll be doing. Has an internal concentration of 1 molar NaCl, 0.8 K2CO3. If our cell was placed in the following solutions, would it cause it to expand, stay the same, or to shrink? Okay, well first, if we have 1 molar NaCl and 0.8 inside of our cell, our little artificial, we're just going to tie it off, it's a bag. Okay, so that is the concentration inside of our artificial cell. We know that our total concentration would be 1.8 molar is our concentration inside of our artificial cell. So we can get rid of this other stuff. We're going to say that our artificial cell has a solute concentration inside of 1.8. So knowing that, if we were to put it in these different solutions, let's see how the water's going to move. Because it tells us up here that our selectively permeable membrane allows water to move, but not ions. And we know that all these guys, our Na and Cl, would dissociate into ions. This K2CO3 would do the same, and all of these KCl's. So all of those would dissociate into ions. So we're looking at how the water is going to move and not the ions. All right, the first one says we have a concentration of 3.6 in the solution outside of our cell. So is water going to move into our cell, or will it move out of our cell? Well, let's think of our little YouTube. We had those pictures that kept coming up. All right, so 1.8, we'll just give that one little ion. 3.6, that's a bigger number. We'll give it 3 little ions over here. All right, if this little tube had some water in it, how is the water going to move to try to make those two sides equal? And what it's really doing is trying to make the concentration the same. So if this side has only one ion, it's going to need less water on its side. So the water will actually move to give you something that looks a little more like this. Okay, because it's trying to dilute this concentration of solutes so that the concentrations are about equal on both sides. So knowing that, this right here tells us that that is a lesser solute concentration than is out here. So the water will move out of our bag. Okay, if the water's moving out of the bag should shrink. And what kind of solution? This is our solution out here. What kind of solution did we just put our little bag in? Well, if the water was leaving the bag, it was a hypertonic solution. Okay. So knowing that, let's look at our other ones. Okay. If 3.6 made it leave the cell, 2.8 should do what? Same thing. Water should leave our artificial cell and making it shrink. Okay. The next one, 2. That is a higher solute concentration, so water should leave again, which is going to make it shrink. All right, our next one, D, says you have a 1.8. Okay, those solute concentrations are the same, so we will have water leaving at the same rate that it's coming in. So when that happens, our cell should stay the same. And what solution is that? Isotonic. All right, and then our last one. If this has a lesser solute concentration than the inside of our cell, then we would expect the water to, oops, not do that. We would expect the water to go toward the higher solute concentration. So water will go into the cell, and if it goes into the cell, it's going to make it expand. And if that's happening, what kind of solution did we just put it in? Hypotonic. All right. So that was just our warm-up. Now let's look at using these equations. You can, whenever you see these on your AP exam, remember you're dealing with the movement of water, and you have all these little trident looking symbols. So it'll make it hopefully easy for you to remember what those go with. All right, so the solute potential, and we have all those equations up here. I is the ionization constant, C is the molar concentration, and remember that those are measured in moles per liter. Okay. And then R is the pressure constant. We got that. Liters per bars over moles per Kelvin. And temperature is in Kelvin. And to get that, you do Celsius plus 273. Got it. What is the osmotic potential of a 0.15 molar concentration of sucrose at atmospheric pressure? And that's important because whenever you see that, that means that pressure is equal to 0. And 25 degrees, what is the water potential? Okay, osmotic potential is the same thing as solute potential. So make a note of that so you don't get those confused. These are the same thing. Solute potential and osmotic potential. So how do you find your solute potential? We have this is a little space. All right, our solute potential equals negative I CRT. All right, so let's just plug in our stuff. Negative, what is I? Well, we're looking at sucrose. And so our ionization constant, this is something you'll make a note of. For sucrose, or any kind of sugar, let's just say sugar, is 1. And why is that? Your sugars are not going to break apart They're not going to ionize because this is the ionization constant. Your sugars are not going to ionize in water, so they have a ionization constant of 1. They're going to stay together in 1 unit. Okay, if we're looking at a salt, well, those guys do ionize. So think of your sodium chloride. When it gets put in some water, it's going to break into its smaller components. So salt has an ionization constant of 2 because it's going to break up into its ions when it's put into water. All right, so down here, sucrose, we know our I value is 1. C is given to us here, 0.15 moles per liter. And that's important because I want y'all to see how your units cancel and what you're left with. All right, R is our constant. We see it right up here, 0.0831. Okay, and the last thing is our temperature, which is 25 degrees Celsius, but we don't need it in Celsius, so we'll say 2, I don't know why it keeps doing that, 273 plus 25. Okay, and that'll be Kelvin. Whenever you work all this out, we see that our moles are going to cancel, our liters are going to cancel, our Kelvin will cancel, and we're left with bars. So our answer, whenever you multiply all that out, your solute potential or osmotic potential, you should find it to be negative 3.7 bars. Okay, so if that's our solute potential, what is our water potential? Well, I'll just keep working over here. Just know it goes together. All right, our water potential my pen died. We know that water potential equals the pressure plus the solute potential. It tells us right here the pressure equals 0. So if this equals 0, then we know that our water potential equals our solute potential. So this right here, negative 3.7 bars, is both your solute potential and your water potential for that one. Okay. Next, what is the osmotic potential of 0.1? This is important. It just changed to sodium chloride from sucrose. Why does that matter? Well, looking up here in our ionization constant, a salt is going to have an ionization constant of 2, whereas our sugar has that ionization constant of 1. So, if the only thing that changed, and as we keep looking, 25 degrees Celsius, 25 Celsius, okay, everything is the same except for we're now looking at sodium chloride instead of sucrose. So, that means, without even working it all out, it means the only thing that changed in my equation is this ionization constant. And it went from 1 to 2, so you would expect your answer to be doubled. And so your solute potential would be negative 7.4 bars, because it's twice of what it was in question 1, because you're now looking at a salt instead of a sugar. Okay. Number 3, which of the above has more water potential. All right, well, we know that all right, we're looking at 3.7 versus 7.4. And so this smaller number tells us that there is less solute there, which gives it a higher water potential. So our answer is going to be this one that came from number 1. Okay, so the smaller number, well, actually, that's the larger number. The larger number indicates that there is less solute in that solution, and so it has a higher water potential. It has more water free to, like, basically surround more solute or to move if it needs to. So this one here, number 1, has more water potential. Okay, so knowing that, which one is more concentrated? Well, question 2 would be more concentrated, because the more solute you add, the lower this number is going to go. So the more solute that you have, the lower that solute potential. You can kind of think of it as the more full it is of solute, the less potential it has to hold more solute. So the lower number is more concentrated because it has a lot of solute already there. And then one that has less solute has more water potential. Okay. If a cell has a pressure of 3 bars and solute potential of negative 4.5 bars, what is the water potential? Well, using the formula, plugging those in, equals 3 plus negative 4.5. So it gives you negative 1.5, and your unit is bars. Okay, that's just plugging in the equation. Number 6. The cell from question 1, okay, is placed in a beaker of sugar water with a solute potential of negative 4.0 bars. In which direction will the net flow of water be? Let's change our color again. Okay, so number 1, we have negative 3.7 bars. And we're putting that in a solution of negative 4.0 bars. So looking at these little rough sketches up here, if we know that the lower number, so that negative 4.0, means it has more solute there, what does that mean for our water? Well, water goes toward the higher concentration of solute, so it should move out of our cell. So it would, in which direction would the flow of water be? It would be out of our cell and into the beaker of sugar. All right, that is looking at the little intro, like level 1 questions, 1 through 6. I want you to work these guys on your own. See what you can come up with.